All right. Yeah. We gotta do this thing. Okay. 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 Why didn't I get it? Okay, that one worked. I don't know why that one worked. Okay, now we gotta do this one. I don't know why it always signs me out. It's annoying as hell, but it's fine. Okay. This is probably signed out. Sign in. For now, let's skip that. Okay. Okay. Okay, this is gonna be Phys 4B quiz 1. All right. Okay. So, all right. So, let's read the first problem. Two free, not held fixed point charges plus Q and plus 4Q are held at a distance L apart. A third charge is placed such that all three charges have zero acceleration. Find the location, magnitude, and sign of the third charge. There's no gravity. All right. All right. So we're going to have like, what? What? Okay. Okay, we have a point here. We have a point here. So we're going to say this is Q1 is equal to a charge with plus Q, and it's at 0, 0. Then we're going to say Q2 is equal to plus... Dude, what's up with the writing on this? This thing is messed up. And let's just say that this is at... let's just do it this way. Now let's say that there's some Q3. So the first thing is to show that Q3 is collinear with with Q1, Q2. Then there will be a non-zero y component force. Thus, that can't cancel or be zero. Thus, system none. Thus, there's a body with non-zero acceleration. Okay. So, position of Q3 is equal to x0 for some x. Now, need to show x is in 0 to L. Okay, there are so we consider forces on Q1. Fe from 2 to 1 and Fe from Q3 to Q1. Okay? It must be by static that sum of F is equal to 0 on Q1. So F2 to 1 plus F3 to 1 is equal to 0. There are two cases that can do this. One, Q3 is to the left of Q1 with same sign. However, this leads to the sum of forces on Q2 now equals 0 because we have two repulsion forces to the right. Add. Two Q3 in 0 to the same argument shows Q3 is not to the, we gotta do this, right of Q2. All right, so we kind of did some of the physics. So now we know that, we basically now know that this diagram is like, good. Okay, so now let's just say, now we know that Q3 must, wait, hold on. We need to add one more thing, which is that and opposite sign. Okay, so now we've determined the sign is going to be, must be minus and between Q1 and Q2. Now, one thing that we need to say here is that this leads to that, hold on, due to Coulomb being a central force. So what I'm saying is, imagine that we had like a charge here and a charge here. If we wanted to negate, so this is, Q1, Q2, Q3. If we wanted to negate this is another way to show that, because the only way to produce something of the same direction, you're going to have something like this or something like this. And then, therefore, if this is F21 and this is F31, then you're going to, you can't add those together and make them 0. So now we know that this diagram is good. Q1, Q2, Q3. So now let's just write all the forces on all of them. I'm just going to write the whole thing out. On Q1, we're going to get F. So wait, hold on. We can also do this. This is going to be X. This is going to be L minus X. So F2 on 1 is going to be equal to K Q1 Q3 over L squared. And then this is actually going to be, we already know this, but this direction, or this is a Q3 and this is Q2, that this is going to be -1, 0. Because we already know the norm of the distance is going to be L of the vector, and then the normalized vector, we know it's pointing to the left. Okay. So we can, and then we're going to have F 3 on 1. And this is going to be equal to, and then this turns into 4Q1, or 4Q rather. So this is going to be, let's actually do some simplification. So I should be able to get rid of that. So we get, it's equal to, oh, wait, hold on. We need to do this the right way. Okay, so we're going to start out with, it's an F equals MA problem. F equals MA problem. Okay, I'm going to box it too. It's important. So now we're going to define our system. Our system is going to be equal to Q1. Okay, so now the forces, F. Okay, wait, let me do this exactly how he wants it. So we have the system, then we have this thing. And is there a way to actually, like, select and grab stuff? I don't think so. Okay, well, that's fine. We're good. So we're going to get F of 2 on 1 plus F of 3 on 1 equals MA. 0 by given. Okay, now we can start to write, and this is going to be a vector, and this is going to be a vector. Now we can scalarize. So F 2 on 1 negative So we're going to get 4kq squared over, let's do big L squared, plus, and this is going to be a minus, right? This is going to be a minus, plus kq over x squared, and then this is going to be equal to 0. Okay, so this is our first equation. So this is equation 1. So we can put a pin in that. Oh, man, it's funny how I just get bigger and bigger at writing. Okay, let's try to make it simpler now. Okay, so now system 2 is equal to, let's say, Q2. Okay, so the forces on Q2 are going to be, so F equals MA. Okay, we're going to have F of 1 on 2 plus F of 2 on, 1 on 3. Let's fix that. F of 1 on 3, and we're going to have 2 on 3. And this is going to be equal to 0, and this is 0 given. Okay. Now we're going to have 1 on 3 plus 2 on 3 minus. So now we can scalarize. So we're going to get okay, so now we can do KQQ over x squared. Should be the exact same force as this, but it should be in the other direction. So wait, this one should push it to the left. This one should push it to the, yes, because this one should push it, if we just assume they're positive, should, so what this means is that so the force of Q3 on Q1 is what we're discussing. And the force of Q1 on Q3 is going to be to the right. Well, but here it's to the left. No, here it's to the right. I think I did something wrong. Let me simplify a little bit of the algebra to check. So we're going to get KQQ over x squared is equal to 4KQ squared over L squared. Cancel these, cancel this and this. Okay, so then we're going to get Q is equal to QX squared over L squared. Then this force should also be negative. Yeah, so we should get okay, so we should get that k q over x squared is equal to minus 4k q squared over L squared. Maybe. I don't know if that's right or not. Okay, so let's just think. The sign on 1 to 3 is going to be a plus. So this is a plus. And then 2 on 3, this is a minus. So we're going to get this minus, and then 2 on 3 is going to be k, 4k q over L minus x squared. Okay, so we should get 1 over x squared is equal to 4 over L minus x squared. We can take the square root of all the sides, and now we get 1 over x is equal to so now we get that's not right though. Damn, how did I already forget how to do this? Okay, let me write it on the full vector thing because otherwise I cannot do this. So if we do, so what is f of 1 on 3? This is going to be k q this is going to be the norm of the vector x0 cubed times x0. Because this is r and that's going to be x0 minus 0, 0 equal to x0. So this is just going to end up being kq over x cubed. How did I do this so wrong? I'm gonna do it on the whiteboard. Okay, so, all right, let's keep going. So I think I had the screen black the whole time, which is just hilarious, but whatever. So I did it on the whiteboard. Now we're doing it now. So what we've done so far is, whatever. I'm just gonna keep going. So the norm L minus X, and then the okay, so we found that, so now we can write the forces, finally. So now we can come down here and we can say, you know, K 4KQ squared over L squared is 10 plus, so we did this, so we know it's a plus. It was always going to be a plus no matter what, because the forces add, they don't subtract together. So now we're going to get K 4KQ, bro, what the hell is going on? Over L minus X squared times 10. And this is really, if you think about it, this is really the zero vector. So you can actually put the zero vector with the harpoon on it. Okay, but now we can scalarize. Scalar. And we can get 4KQ squared over L squared plus 4KQQ over L minus X squared is equal to 0. So now it's scalarized, right? So now it's just a scalar equation. So the first thing we're going to do is we're going to cancel some stuff. So we're going to cancel this, 4KQ. So we're going to get Q over L squared. Let's say Q over L minus X squared is equal to minus Q over L squared. And actually, let's do it even one more step. We're going to get Q is equal to minus Q over L squared times L minus X squared. Okay, I'm just going to bring that, up here. So we're going to get, we got that X equals sub X equals L over 3. So then we're going to get minus, oh my God, minus Q times L minus L over 3 squared over L squared. This is going to be equal to minus Q over L squared times 2/3 L squared, which is equal to minus Q over L squared times 4, over 9L squared. These L's cancel, and then we get Q is equal to minus 4 over 9Q. All right, we did it. All right, so that first problem is good, and I want to get in the habit of doing this. The problem is when it becomes a real two-dimensional problem, it becomes a total freaking mess. Okay, that's problem 1. Okay. Let's do problem 2. So the only ones we have to do are 1, 2, 4, and 7. The electric field one we don't have to do. But then on here, I want to look at these problems. Although if they have to do with electric fields, we're not going to do them. But if they're just pure Newton's second law problems, we're going to do them. And then torque. We're going to do these 7 torque problems. And hopefully I can do well on the quiz. All right. Problem 2. 2 small conducting balls, each of mass m, are hung from a silk thread, each of length L, and carry similar charges and are in equilibrium. Assume that the angle of separation between the 2 threads is a small angle theta. Find the charge on one ball. There is gravity. Okay. So I'm just going to go. The thing is, I've done this problem before, but let's just try to do this. You might not be able to see. Yeah, that's not going to work. But maybe you can hear me? I don't know. I'm going to do it on the board, though. What is the problem asking us to find? The problem is asking us to find the charge. Okay. Okay. This is Q. Let's just say this is 0, 4. Okay. So this is going to be L sine. Okay, so this is going to be. Switch it over. I didn't finish it. I got stuck. I'll show you where. Okay. Is this sine A? Yeah, it's sine A. Okay, so I think actually that's pretty good uh part. So let me just the x component is going to be sine and Okay, so let's do that. Okay, I think I got the. I think I can do it. So let's do. Let's find some space here. All right, so we got problem 2. Okay, so let's just draw it out. All right, so the first thing I'm going to do is I'm going to say Q1 is equal to Q0, 0, origin. Then I'm also going to say mass M. And let's also do this. So we have the gravity force. So we're going to say G vector down. Okay, then we're going to make a coordinate system. So we're going to say X plus Y plus. Okay, and then this is going to be their second charge, and this is going to be equal to Q. And then now we have a kind of a conundrum. What is the coordinate of this? We don't know. So we do know, however, that this is called A. Okay, so now, and we know that this is length L. So now we can just say that this is going to be equal to 2 minus 2L sine A. And then the y component is 0 because these are level. Now it's like, actually, how do we know? Maybe need to justify. So, we know horizontal because the charges, oh yeah, mass M. All right, so just because of that, just because the charges and the mass are equal, we're good. All right, so now it's pretty obvious to me that this is an F equals MA problem, so I'm just going to write F equals MA. All right, now we're going to take the system equal to Q1. Okay, so what are the forces? All right, let's do the forces. So we're going to have this is Q1. We're going to actually clean that up. Q1. Okay, so we're going to have a force going this way called FT. Then we're going to have a force going this way called FE. And then we're going to have a force going this way called FG. These are the three forces. So now we know that FT plus FG plus FE is equal to 0. This is 0 given. Okay, is it given? I don't know. Or in equilibrium. Okay, so we're good. Okay, now, all right. So now we kind of get into some of the physics. So, first, I'm going to define T is equal to norm of FT, total tension force. This is a scalar. Okay, then we're going to say FTX is equal to T sine A 0. FTY is equal to 0 T cos A. And this is actually a minus. Okay. I think actually the better approach, ignore all this. Oops. I wish there was like a better way to delete. This is such a stupid way to delete. Okay, so a better way to do this is FG and FE each aligned along an axis. So, since i.e. FG dot FE is equal to 0. Perpendicular, right? Perpendicular. There is only one other force. The x component of tension must cancel electric, and y of tension must gravity. Okay, so where do we go from here? We go from here is to split problem component wise. So we're going to say that ftx, and this is a scalar, it's just the plus fe is equal to 0. fty plus fg is equal to 0. Okay, so and then this one's going to be so first off, let's just do this. Oh yeah, and the problem, find the charge. Okay, so oh yeah, and then just remember small angle approximation. Small angle approximation is sine A equals A, cos A equals 1. So therefore, tan A equals A. All right. So what I'm going to try to do, I think, is let's just get this cleaned up. So KQ squared over 2L sine A squared is equal to T sine A. So now I'm going to just put this in here, I think, and just get mg sine A over cos A. This goes to A. This goes to A. So now we're going to get KQ squared over 2, or let's just do this, 4L squared A squared is equal to mg, right? Because this becomes tan, which becomes A. mg so then this becomes this becomes Q squared is equal to mg 4L squared A squared over KQ squared. Or not KQ squared, just K. So then Q is equal to two LA times square root of mg over K, which is equal to Q is L theta times mg over K. Is that it? I don't know. I messed something up. I messed up this 4L Q squared is equal to 4L A cubed. Oh, because we missed an A on this side. Wait, did we? We missed an A, so then this is going to be A cubed. Okay. So now we get Q is equal to 2, or actually let's do this. The hell is going on? Okay, so we're gonna get 4 times A cubed is gonna be equal to 4 times theta over 2 cubed, which is equal to 4 theta cubed over 8, right? Which is equal to theta cubed over 2. What happened here? Oh, no. Okay, never mind. Just a bunch of algebra, bro. It should be enough to just find q squared, but... So then we're going to get 2L square root mg over k times theta over 2 to the 3 halves. Okay, this is just the algebra. All right. That's good. Maybe at the end of this, we'll do this one more time just to, make sure that it's all good. But that was a fun one. That one was actually easier than the other one, I think. Because you don't have to solve two systems really. Or I guess you kind of do, but not that bad. All right, problem 3 is nothing. Problem 3 is just calculating. Problem 4, this one is the one that I really need to get. This is the first time I'm doing the torque thing. And, if I'm going to do it, like, we should probably do this, at least one time with the problem 4, but with actual presumably we have to make them 3 vectors. Let's see. I just want to... We're not going to be taking determinants because we don't need to for class yet, but what I do want to do is... make sure that I at least see it so that I'm not, like, confused what the real thing is. Oh my god, man. What the hell's going on? Did I get a chat message? I never get chat messages. You said something. Eminence. Alright, we good? What the hell? This thing is broken. Alright, we gotta open it again because it's fucking broken. What is happening? Oh, it's still doing a bunch of shit. Dude, look at this. Fucking 80 seconds. Fucking insane. And then it takes a forever to... Dude. I like it. It's just so bad all the time. It's like, also, why I literally had this open a few days ago. Why are you giving me issues? What is the holdup? God, it pissed me off so much. Now they decide to fire. Fucking 80 years later. Okay, I think we're good now. Good. Okay, so we have a charge, which is just basically a scalar and then a position, and that's just some vector in Rn or something. I did the same with mass, but I don't really know if that's like I don't really know if that's like important. Okay, all right, let's make some charges. Okay. All right, so here we go. So what I want to do, did I put linear algebra in here? Okay, so what I want to do is cross. Okay, good. So this takes vectors in R3 specifically, right? Compute the cross product of 2, 3 vectors. Okay, good. Oh, this is a good example because look, we have something in Y and something in Z, and it's giving us uh, it's giving us so. How do you do this? So we have this. So this is Y, this is Z, and it's giving us this. And if you go like this, and you have to be, the order is important, right? Because what we want is, no. Shouldn't it be this way? A cross B is this way. A is this way, B is this way. I feel like it should be -1. Oh wait, actually, let's make this Z and this Y. Okay, so that one makes sense. But it's anti-symmetric, right? So that means that if I go like this, then it's like that. But if I go like this, then it's like that. So then it's 1, 0, 0. Okay, I got it. I got it without having to ask ChatGPT. Okay, this makes sense. So if you're, this is A, this is B, then this is the cross product. But if you do doot doot, it's that way. Okay, I got it. That's the whole example. That's crazy. All right, so it needs to be 3 vectors. So I think what we need to do is add zeros to all of these. Okay, and so now what we want to do is just start off by computing the torque. Okay, so first off, the force. The force of Q4 on Q1. Okay, and it's R cross D. So now, but it's from the origin. So 0 of Q1 dot pos, something like this. Okay, so origin. So now what we want to do is R, is it called displacement? From to. So from the origin to the point of the force, right? So the origin Q1 like this. I didn't do something right. Hold on. Displacement. Oh, because this needs to be a charge. I think, yeah, that's the problem with making new types. We should just be able to do origin minus Q1 dot pos like that. No, I messed it up. Wait. In the torque formula, we have R cross F. And R is the vector from a point to the point that the force F is applied. Right? If a pivot is the origin and a tangent force applied. In the torque formula, R cross F, R is the position vector from the point you're taking moments about to the point where force is applied. Yeah, it's super interesting that, like, yeah, so torque is always relative to a point. That's kind of the, like, interesting thing about torque. Okay, so now that we have R, so we should just be able to say this. Then we should be able to do R cross. What the frick? Why does this thing never work? Language server is so broken, dude. Whatever. I don't actually. None of my concern. Oh, dude, you've got to be kidding me. That is so annoying. All right, we're just not going to do that. We have to do it over here because. Oh, actually, I need to download this because this is so sick. Share, publish. Can I publish this? If I publish it, dude, wait, that's actually so sick. Do I have like a public profile where I can just like go to all my published work? Aw. So I can't like go to my account? That's annoying. That would be so sick. I love when people do that. Okay, good. So, so I got like real into a bunch of crap that I don't need. So let's go all the way back up to before I was messing with rules. Yeah. Okay. So the main thing here, we have a charge, we have another charge. Then we have this rule. This code is the thing and now we get here, this vector where we have a distance L apart and whatnot. Did I ever write the F matrix thing? I probably did, but I'm not going to worry about that. All right, so this is the good stuff. This is all we need. So now let's just, if I do cross, is this going to be the cross product? Or is it going to be something weird? Evidently, it's nothing. There we go. All right, so if I do this, cross 0, 1, 0, like we just did, 0, 0, 1, we should get 1, 0, 0. So what we just did is we went this way, and then this way. So we went like that, and we got 1, 0, 0. Good. Okay, so now let's figure out what the so let's set up the problem, because clearly, I mean, like, come on, you know, when are they gonna get their stuff together? That's my question. So first off, can we just do this? We're gonna say Q1 is equal to charge Q minus L over 2, 0. And we need to make this actually 0, 0, 0. So now we want the pos of the charge. So let's try this. So we do this, and let's do pos of Q1. Works as intended. All right, so now we need the force between, all right, so let's make the second charge. Charge Q as well. Let's just make it simple. This is going to be minus L over 2 minus H, 0. There's no Z component. Okay, so, and now we have FQ2 Q1. So F, yeah, well, it's ambiguous no matter what. We'll just do F21 is equal to F of Q2 on Q1. And the force is in the y direction. Okay, so now we have the force, and it's a 3 vector, which is good. Now all we need to do is R is going to be equal to the distance from the origin to the first charge. So it's going to be, you know, pos Q1 minus, is there a 0? You know, let's just do this. Is there an origin? I don't know. Okay, obviously you don't really need to do this if it's 0, 0, 0, but I want to do it. I want to do it. All right, so now we can do cross RF 2, 1. So it's negative. So hold on, let's think about it. Because I'm going like this and this. So the torque is going negative into the screen. But if I were to do this, if I were to do this, Q3 is equal to minus Q. And then I did F31, or the force of 2 on 3 is equal to F Q2 Q3. And then I changed this. It's the same position, so R doesn't change, but this changes. Then we're going to get positive torque, because then we're curling this way, then this way, and we got this, which my thumb is pointing towards me. Torque you, bro. Torque you. All right. So, and it's nice that we're not going to have to do any 3D torques. So, it's always going to be just nothing in X and Y and purely in Z, I think. Okay, I'm going to go to the bathroom. Hold on, I got to do something. Maybe it does need water. Let me move this stuff out of the way. Okay, it got too dark. I need to go inside. I'm going to finish the torque problem in a minute.